Hello students, this is Professor Chalai, and in this video we're going to go over bomb calorimetry. As always, you can follow along with our Chapter 5 workbook. By the end of this video, you should be able to describe a bomb calorimetry experimental setup and also perform bomb calorimetry calculations. Let's get started. So the bomb calorimeter is very similar to the coffee cup calorimeter that we looked at earlier in the semester with some key differences. So let's compare the two. So bomb calorimetry, we have this enclosed casing that the experiment is carried out in, similar to the coffee cup calorimeter, where we have a styrofoam coffee cup, for example, that helps to insulate the heat. In the coffee cup calorimeter, we have a thermometer, right? And we also have a thermometer in the bomb calorimeter to measure the increase or decrease in temperature of the calorimeter. We also have some sort of stirrer, which we also did in the coffee cup calorimeter to sort of stir the solution. And we have water, of course, as sort of the majority of the calorimeter. In the coffee cup calorimeter, it was also filled with water, mostly because water has a high heat capacity, so it takes a lot of energy to change the temperature of the water. And in the coffee cup calorimeter, we would have carried out the experiment inside of the solution. That's where the differences for the bomb calorimeter start. In the bomb calorimeter, we have this bomb, as it's called, inside of the bomb calorimeter where the reaction is carried out. And specifically, the reaction that is carried out is a combustion reaction. So combustion reaction. Now for a combustion reaction, as we talked about earlier in the semester, it's burning something or exploding something in this case with oxygen. So in here you'll have your sample and the chamber is filled with oxygen gas, and there's an ignition wire to sort of ignite that and start the process going. So you will ignite the wire, the sample would start to combust or burn with oxygen. There's excess oxygen, so the sample will give us the theoretical, will be the limiting reagent. And then as this reaction happens, as this burns, it'll heat up the water and the temperature will go up, and you'll measure that with the thermometer. Now, another key difference here is that this whole setup is sealed. Whereas in a coffee cup calorimeter, right, the air is not necessarily sealed, so the air can escape. So this leads to one very important difference with a bomb calorimeter versus a coffee cup calorimeter. So in a coffee cup calorimeter, we measure the heat transferred, Q, right? So this is coffee cup. In the bomb calorimeter, what we're measuring is the energy change. And here's why. In our next lecture, we'll go over this in a little bit more detail, but the change in energy of the system is related to the heat flow and the work done on the system. And as we'll learn, the work comes from negative of the pressure times the change in volume. However, this whole system is sealed. So all of the heat energy gets transferred, all of the heat that's transferred, we can assume comes from the energy released from the reaction, and nothing else happens. So the only difference then is the energy for the system. So the heat for the system will be negative the heat from the calorimeter. We talked about that. The system in this case is the reaction, so we can write the heat from the reaction is negative the heat from the calorimeter. But because all of the heat goes into the energy, we can write the energy, the change in energy for the reaction comes from negative the heat from the calorimeter. So that's one important difference. For bomb calorimeters, we're measuring the energy from the reaction, and specifically the type of reaction that we're looking at, as I mentioned, was the combustion reaction, which is reaction with oxygen. So for example, in number 12, when we talk about the combustion of C12H22O11, right, that's C12H22O11, which is solid, sucrose, we're reacting this with oxygen to form carbon dioxide, water vapor, and other stuff. The combustion reaction. This is, of course, not balanced. So those are the differences between a bomb calorimeter and a coffee cup calorimeter. So we need to remember that the change in energy of the system, or the reaction, because the reaction is the system we're interested in, will be negative the heat from the calorimeter. Okay, let's look at some problems involving a bomb calorimeter calculations. Number 12 asks us, tells us that 1.010 grams of sucrose undergoes combustion in the calorimeter and the temperature rises from 24.92 to 28.33 degrees Celsius. So already we're thinking we have an initial and a final temperature. So initial temperature is equal to 24.92 degrees Celsius. The final temperature is 28.33 degrees Celsius. And it's asking us to find the delta E for the reaction in units of kilojoules per mole. So that's going to become important, and kilojoules per mole of sucrose. So I'm going to highlight that. Kilojoules per mole of sucrose. Okay. Tells us the heat capacity of the bomb calorimeter as 4.90 kilojoules per degree Celsius. So that's another difference that we might want to take into consideration. The heat from the calorimeter, usually for a coffee cup calorimeter, we measure this as the mass of the water times the specific heat capacity of the water times the temperature change. However, because the calorimeter is made up of more than just water, there's other pieces of equipment in there that can absorb energy. We would replace the mass times the specific heat with just the heat capacity, C, of the calorimeter. So this is the one difference. So we don't have to work with the mass of the calorimeter, we just have the heat capacity of the calorimeter. So the heat capacity of the calorimeter in this example is 4.90 kilojoules per degree Celsius. It's in kilojoules, not joules, because usually we're dealing with larger amounts of heat for a bomb calorimeter. All right, so if we have this, then we can go ahead and find the heat from the calorimeter using this equation, right? So the heat from the calorimeter, Q from the calorimeter, would be the heat capacity, 4.90 kilojoules per degree Celsius, times the temperature change, which is the final temperature, 28.33 degrees Celsius, minus 24.92 degrees Celsius. The things in the parentheses, the temperature change would come out to be, well, let's plug all of this into our calculator. And the degree Celsius would cancel out with the degree Celsius there, and we get a heat from the calorimeter of 16.7 kilojoules, right? Because that's the units that the units that the heat capacity was in. All right, so this is the heat from the calorimeter, which means that the energy for the reaction will be negative the heat from the calorimeter. So it will be negative 16.7 kilojoules. Now, a couple of things I want you to notice. The heat from the reaction is negative, which means the reaction lost heat, which makes sense because the water in the calorimeter increased in temperature. So the energy from the reaction went to increasing the water in the calorimeter, the temperature of the water in the calorimeter. However, like we saw here, we want that delta E for the reaction in moles of sucrose. Why is this important? Well, if you burn 1 mole of sucrose versus 2 moles versus 3 moles, the amount of heat or energy that you have from that reaction will be very different. So to make sure that we're all talking about the same sort of thing, we'll standardize it by expressing it in terms of 1 mole of sucrose. So in order to do that, we need to figure out how many moles of sucrose we have right now. So let's do that. So the number of moles of sucrose that we used, sucrose, would be, we started with 1.010 grams, and we need to divide by the molar mass of sucrose, which I assume that we all know how to do, so I'm not going to show you that, but I calculated to be 342.3 grams of sucrose per moles of sucrose. So that will give us a number of mole equal to 0.002951 grams of sucrose. Sorry, moles of sucrose. There we go. So we have the delta E for the reaction, the energy from the reaction. We have the amount of moles of sucrose. So the delta E for the reaction divided by the moles of sucrose would be minus 16.7 kilojoules divided by 0.002951 moles of sucrose, which will be negative 566 to 360 to 3 significant figures kilojoules per mole of sucrose. And that's it. That's our answer. So negative large number minus 5660 kilojoules per mole of sucrose. So let's go over those steps again. We had the temperature change. We have the specific heat, the heat capacity of the calorimeter, which means we can calculate the heat from the calorimeter. The heat from the reaction is negative the heat from the calorimeter, but we need to express that in terms of moles of sucrose. So we then found the moles of sucrose, divide the heat from the reaction by the moles of sucrose, and so the delta E for the reaction in terms of kilojoules per mole of sucrose is minus 5560 kilojoules per mole. All right, hopefully that all makes sense. I would like you to try numbers 13 and 14 by yourself. Pause the video now, work that, and then when you're done, I'll go over the answer with you. Okay, let's look at number 13. We have another reaction. Hexane is undergoing combustion in a bomb calorimeter. We have the temperature change, 25.87 to 38.13 degrees Celsius. And they want us to calculate the delta E of a reaction in terms of kilojoules per mole of hexane, and they give us the heat capacity of the calorimeter. So we can figure out the heat from the calorimeter, which will be the heat capacity, right, of 5.73 kilojoules per degree Celsius, multiplied by the temperature change. So the temperature change here is 38.13 degrees Celsius minus 25.87 degrees Celsius. So degrees Celsius cancels out, and we get a heat from the calorimeter of 70.2 kilojoules. Okay, so that means that the heat from the energy from the reaction will be negative of this, so minus 70.2 kilojoules. But we want that in terms of kilojoules per mole of hexane, so let's figure out how much moles of hexane that we have. So our moles of hexane would be the mass of hexane, which is 1.550 grams, divided by the molar mass of hexane, which I calculated to be 86.18 grams per mole. I trust everybody knows how to find molar mass by now. And so we get 0.01799 moles to 4 sig figs. So that means that the energy for the reaction per mole of hexane would be equal to the energy minus 70.2 kilojoules. So minus 70.2 kilojoules divided by 0.01799 moles of hexane, which will be equal to minus 3902, whoops, sometimes my pen freaks out, minus 3902 kilojoules per mole of hexane. But we need this to 3 sig figs, and this is 4 sig figs, and so the only way to make this 3 sig figs would be minus 3.90 by 10 to the 3rd power. Okay. I hope you got that answer. Let's look at number 14. If you haven't worked it out yet, please do pause the video, do so now, and then unpause the video, and I'll work it out with you. Okay, here we're looking at the combustion of toluene, and it tells us the heat from the reaction in kilojoules per mole, and they tell us how much toluene we have, and they tell us that they tell us the temperature change as well. And what they're asking for is the heat capacity of the bomb calorimeter. So if we write the heat from the calorimeter as the heat capacity of the calorimeter times the temperature change, they're asking us to find the heat capacity of the calorimeter. So let's rewrite this equation just to solve for that. So if I divide both sides by delta T, we will see that the heat capacity of the calorimeter is the heat from the calorimeter divided by delta T. Okay, so let's figure out what the heat from the calorimeter is and what the delta T is. We can figure out delta T easily, right? Because they give us the temperature change. So delta T will be equal to 37.57 degrees Celsius minus 23.12 degrees Celsius, which will give us a temperature difference of, let me just punch this into my calculator, 37.57 minus 23.12, that gives a delta T of 14.45. degrees Celsius. Okay, so we have delta T. Now we need to figure out what the heat from the calorimeter is. So remember that the energy from the reaction, there we go, the energy from the reaction will be negative the heat from the calorimeter. Right, so if we can find the energy for the reaction, we can find the heat from the calorimeter. They give us the energy of the reaction here in terms of kilojoules per mole. So the energy for the reaction will be minus 3.91 kilojoules per mole, but we need, this is for 1 mole, we need it for the amount of moles of toluene that we have. So now we need to find the number of moles of toluene. So number of moles of toluene is equal to 1.55 grams divided by the molar mass of toluene, which happens to be 92.14 grams per mole, which comes out to be 0.0168 moles. So let's use that. Let's use that here, 0.0168 moles. So this will give us an energy for the reaction in terms of just kilojoules of negative 0.0657 kilojoules. So that's the delta E for the reaction. So now we mentioned that the delta E for the reaction is negative the Q from the calorimeter. So the Q from the calorimeter will just be positive 0.0657 kilojoules. Okay, so now that we have the heat from the calorimeter and the temperature change, we can actually now find the specific heat capacity of the calorimeter, which is just going to be the heat from the calorimeter, which is 0.0657. So this is 0.0657 positive kilojoules divided by the temperature change, 14.45 degrees Celsius. So 14.45 degrees Celsius. And so this will give us a heat capacity of 0.00455 kilojoules per degree Celsius. Or, because this is such a small number, we can just write this as 4.55 joules per degree Celsius, right? By converting 1 kilojoule is 1,000 joules. So that's our specific heat capacity of the heat capacity of the calorimeter, not specific heat capacity. All right, I hope this was all clear. If you have any questions, please let me know. In our next video, we're going to talk about enthalpy. I'll see you then. Bye.